In the grand, silent theater of the cosmos, our solar system is a tiny, familiar stage. We know its actors, the planets, the asteroids, the comets born in the cold, distant dark. But in early July 2025, an unscheduled performer burst onto the scene, an intruder from an unknown stage light years away. It was first spotted by the Atlas Survey telescope in Chile, a sentinel programmed to watch for dangers closer to home. But this was no ordinary threat. This was 3I/Atlas, the third interstellar object ever detected, a visitor from the vast, mysterious gulf between the stars. It was immediately clear this was no ordinary comet. It was moving at a blistering 58 kilometers per second, a speed far too great to be gravitationally bound to our sun. It was a true celestial tourist, destined for a single, fleeting pass through our neighborhood before vanishing back into the interstellar void. Unlike its famous predecessor, the bizarre, cigar-shaped Oumuamua, 3I/Atlas looked at first glance like a comet, but as we would soon discover, it was a comet unlike any we had ever seen. Its arrival triggered a global scientific scramble, a race against time to study this messenger from another star system before it disappeared forever. What secrets did it carry? And what could it tell us about the universe beyond our own cosmic backyard? The overall tone should be that of a high-quality, cinematic science documentary. Start with a sense of urgency and discovery. Transition to an analytical, educational, and awe-inspired tone when explaining the science. Build suspense and intellectual tension during the Loeb controversy. Conclude with a feeling of wonder and anticipation for the future of interstellar exploration. Pacing should be deliberate, with clear pauses to let complex information sink in. The challenge was immense. Unlike a domestic comet on a predictable elliptical orbit, 3I/Atlas was on a one-way hyperbolic trajectory. We had one shot to get it right. From the moment of its discovery, the world's most powerful eyes turned towards this faint speck of light. It became a target of opportunity, a designation that allows astronomers to bypass months of scheduling queues for telescopes like the Hubble. The opportunity was too precious to miss. Hubble captured its first images on July 21st, when the comet was 446 million kilometers from Earth. The streaky stars in the background of the image told a story of immense speed. These observations were crucial. They allowed scientists to finally measure the comet's icy heart, its nucleus, pinning it down to a diameter between 440 meters and 5.6 kilometers. This was a vital correction. Early estimates, based on its brightness alone, were far larger. Hubble revealed that much of the light was coming from its coma, the cloud of gas and dust surrounding the nucleus, not the nucleus itself. The giant was a ghost. While Hubble provided the sharpest view, the James Webb Space Telescope provided the deepest insight. On August 6th, JWST's near-infrared spectrograph was pointed at the visitor. A spectrograph is a scientific prism. It breaks light down into its constituent chemical fingerprints. The results were astounding. JWST found a complex coma morphology, a layered, intricate cloud of outgassing. At this stage, far from the sun, the comet was breathing out carbon monoxide and carbon dioxide more than water, a hint that it came from a place much colder than the birthplace of our own comets. But the story had another twist. Astronomers working with NASA's Transiting Exoplanet Survey Satellite, or TESS, made a startling realization. While its official discovery was in July, TESS, a telescope designed to find planets around other stars, had unknowingly photographed the comet months earlier, starting in May. This pre-discovery data was a goldmine. It provided a crucial baseline, a record of the comet's behavior as it journeyed into the inner solar system. And it revealed something that would become one of 3I Atlas's greatest mysteries. The team, led by Adina Feinstein, analyzed the TESS data. Between May and June, the comet moved 0.9 astronomical units closer to the spacecraft. Based on proximity and increased solar reflection, they calculated its brightness should increase by a factor of 1.5. Instead, it surged by a factor of 5. The comet wasn't just reflecting light, it was dramatically and actively brightening, far more than expected. This suggested 3I Atlas was hyperactive, potentially releasing exotic, hypervolatile ices like frozen nitrogen or hydrogen when it was still a staggering 6 astronomical units from the Sun, near the outer limits of where even the most active comets in our system begin to wake up. Confirmation poured in from the ground. The TRAPPIST telescopes in Chile and Morocco reported similar brightness values. The Gemini South telescope in Chile not only captured stunning multicolor images showing a rapidly growing tail, but its spectrograph detected the unmistakable signature of cyanide, CN molecules, being released from the nucleus. A cosmic detective story was unfolding in real time, with observatories across the globe acting as the investigators. Every new piece of data made 3IA Atlas stranger. It wasn't just its hyperactivity, it was its very essence, its chemical makeup that set it apart. The discovery of cyanide was expected, but what scientists found next was not. By measuring the ratio of dicarbon, C2, to cyanide, they found that 3IA Atlas was one of the most carbon chain depleted comets ever observed. Now, why does a detail like carbon chain depletion matter so much? Because studying the chemistry of an interstellar object is like a form of cosmic archaeology. These comets are pristine relics, time capsules from the birth of their own solar systems. They're formed in the protoplanetary disk of gas and dust that surrounds a young star. The chemical composition of that disk, its temperature, density, and elemental mix, gets locked into the ices of the comet. When we analyze a comet from our own solar system, we are studying the chemistry of our own primordial past. But when we analyze an interstellar comet, we are performing an extraordinary feat. We are studying the chemistry of another star system, light years away. We are getting a glimpse into the building blocks of a completely alien planetary system. The fact that 3IA Atlas and Borisov before it were both carbon chain depleted suggests that the chemistry of their home systems might be fundamentally different from our own. It could mean they formed in a much colder region of their disk, or that the disk itself had a different chemical starting point. Each molecule we identify is a clue, a single brushstroke in a portrait of a star system we will never see directly. This is why these visitors are so profoundly important. They are messengers carrying the ground truth of other worlds. And the strangeness didn't stop with its chemistry. The final and perhaps most baffling discovery came from how 3IA Atlas played with light itself. On September 5th, a paper was published presenting the first ever polarimetric observations of the comet. Polarimetry is a specialized technique that measures the orientation of light waves as they scatter off a surface. It can tell us about the texture, size, and structure of dust grains in a way no other method can. The results were unprecedented. 3IA Atlas exhibited an exceptionally deep and narrow negative polarization branch. To put it simply, the light scattering off its dust grains was behaving in a way that has never been seen before in any other comet or asteroid in our solar system. Even Borisov showed a more normal positive polarization. This single measurement placed 3IA Atlas in a class of its own. It wasn't just a different flavor of comet, it was a fundamentally different kind of object. The dust grains in its coma were unlike anything we had ever encountered, hinting at a formation process or environment completely alien to us. The messenger was not only carrying a secret message, it was made of a material we didn't recognize. With so many anomalies, it was perhaps inevitable that speculation would move beyond the natural. And into this scientific whirlwind stepped Avi Loeb, a renowned and respected astrophysicist from Harvard University. Loeb is also known for his willingness to explore controversial, outside-the-box ideas, most famously his hypothesis that Oumuamua was an alien artifact. With 3I Atlas, he saw another opportunity to challenge the scientific consensus. Loeb's argument began with the early, overestimated size of the comet, around 10 kilometers in radius. He argued that an object this large from interstellar space should be an exceedingly rare event, based on our understanding of how much material is drifting between the stars. The odds, he suggested, were suspiciously low. From this statistical improbability, he made a leap. Perhaps it wasn't a natural object. Just days after the discovery, Loeb and his collaborators published a paper with a title that sent shockwaves through the media. Is the interstellar object 3I-Atlas alien technology? The paper placed the alien speculation front and center. It explored the possibility that the comet was a technological probe, possibly hostile, referencing the dark forest solution to the Fermi paradox, the idea that advanced civilizations stay silent and hidden for fear of being destroyed by others. The authors stated they were exploring the idea for educational purposes and because it is fun to pursue. They analyzed the comet's astrodynamics, suggesting its flyby of Venus, Mars, and Jupiter was non-coincidental and could have been engineered. They maintained that its large size pointed to an artificial origin. However, the scientific process is built on evidence and peer review, and the mainstream astronomical community quickly moved to rebut Loeb's claims. The most significant counter-argument came from the very data being collected. The Hubble press release on August 7th, which revised the nucleus size down to a much more modest 5.6 kilometers at most, completely undermined the core premise of Loeb's statistical argument. Yet even in subsequent posts and papers, Loeb continued to reference the outdated larger measurements to support his hypothesis. Other scientists, like geoscientist A.K.M. Ehsan-ul-Haq, published papers demonstrating that the comet's trajectory could be perfectly explained by natural gravitational dynamics. There was no need to invoke engineered maneuvers. The hyperactivity, the brightness surge, the strange composition, all were puzzling, but all had potential natural explanations rooted in chemistry and physics, however exotic. The controversy highlights a fundamental tension in science, the balance between imaginative speculation and rigorous, data-driven analysis. For many of Loeb's critics, it was a lesson against jumping to conclusions. Crying aliens is exciting, but the scientific method demands that we exhaust all natural explanations first. By waiting for the dust to settle, both literally and figuratively, we ensure that if and when we do find true evidence of extraterrestrial intelligence, our claim will be built on a foundation of undeniable fact, not just tantalizing, but unsubstantiated speculation. As 3I/Atlas prepared for its closest approach to our Sun, its perihelion, on October 30th, it left a trail of profound discoveries and lingering questions. It forced us to reconsider the diversity of cometary objects in the galaxy. It provided a live-fire stress test of our rapid response observation capabilities, and it delivered a precious, tangible sample of the chemistry of another star system. We now know that interstellar space is not entirely empty. It is populated by these wandering pilgrims, each a unique time capsule from its home. 3I/Atlas has shown us that these visitors can be hyperactive, chemically strange, and composed of dust unlike anything in our own cosmic neighborhood. It has taught us that the building blocks of planets may vary more from star to star than we ever imagined. On the day of its perihelion, the comet was too close to the Sun to be observed from Earth, hidden in the glare of our star. But this was not goodbye. It is predicted to re-emerge into view by early December, ready for a renewed bout of intense analysis. Missions like NASA's SOHO and Sphere-X, along with continued observations from Hubble and Webb, will be waiting. As 3I/Atlas takes its final bow and disappears behind the solar curtain, it leaves us to ponder its final secrets. How much more will its activity change as it recedes from the Sun? Will the thermal stress cause it to break apart, exposing fresh, untouched ices from its core? And can we, by tracing its trajectory back into the void, ever hope to identify the star it once called home? The race against time to answer these questions continues. 3I/Atlas was more than just a rock from deep space. It was a messenger, a puzzle, and a profound reminder of the vast unknown universe that lies beyond our familiar shores. Its fleeting visit has permanently enriched our understanding of the cosmos, leaving us to wonder with more anticipation than ever before, who will be the next visitor, and what story will they have to tell? As 3I/IATLAS prepared for its closest approach to our Sun, its perihelion on October 30th, it left a trail of profound discoveries and lingering questions. It forced us to reconsider the diversity of cometary objects in the galaxy. It provided a live-fire stress test of our rapid response observation capabilities, and it delivered a precious, tangible sample of the chemistry of another star system. We now know that interstellar space is not entirely empty. It is populated by these wandering pilgrims, each a unique time capsule from its home. 3I/Atlas has shown us that these visitors can be hyperactive, chemically strange, and composed of dust unlike anything in our own cosmic neighborhood. It has taught us that the building blocks of planets may vary more from star to star than we ever imagined. On the day of its perihelion, the comet was too close to the Sun to be observed from Earth, hidden in the glare of our star. But this was not goodbye. It is predicted to re-emerge into view by early December, ready for a renewed bout of intense analysis. Missions like NASA's SOHO and Sphere-X, along with continued observations from Hubble and Webb, will be waiting. As 3I/Atlas takes its final bow and disappears behind the solar curtain, it leaves us to ponder its final secrets. How much more will its activity change as it recedes from the Sun? Will it thermally stress cause it to break apart, exposing fresh, untouched ices from its core? And can we, by tracing its trajectory back into the void, ever hope to identify the star it once called home? The race against time to answer these questions continues. 3I/Atlas was more than just a rock from deep space. It was a messenger, a puzzle, and a profound reminder of the vast, unknown universe that lies beyond our familiar shores. Its fleeting visit has permanently enriched our understanding of the cosmos, leaving us to wonder with more anticipation than ever before, who will be the next visitor and what story will they have to tell? For a few brief months, our world of science, debate, and discovery was completely captivated by a visitor from an unimaginable distance. We pointed our greatest instruments at it, analyzed its every breath, and debated its very nature. And soon it will be gone, a fleeting memory on its eternal journey. Its passage serves as a powerful reminder. As we look out into the vast darkness, searching for messengers like Three-Eye Atlas, we must also remember what those messengers would see if they looked back at us. They would see a single tiny point of light, a pale blue dot, home to every person you've ever known, every triumph and tragedy, every king and peasant, every creator and destroyer of civilization. These interstellar encounters do more than just teach us about other worlds. They teach us about our own. They contextualize our existence, highlighting the profound isolation and the precious rarity of our shared home. In the grand, silent cosmic theater, our planet is the only stage we have. And visitors like Three-Eye Atlas are the universe's way of reminding us to look after it and each other.